Hello everybody and welcome back. Root Beer here looking at question 5 on the 2015 Manitoba Math Contest. If you'd like a copy of this contest, of course, click the very first link in the description as with all my contest videos, and you'll get yourself a copy that you can try these questions out on your own. So, 5a. Find all possible values of a such that the line with equation x plus y equals a is tangent to the circle with equation x squared plus y squared equals 25. Okay, so this circle we can read off from its equation. Its center is at the origin. It's nice, symmetric. That's a terrible circle. I'm going to draw the circle first and then the axes. You'd think I'd have learned by now. Circle, axes. Oh, that's a much better picture. Love that picture. Okay, good picture. Alright, so x plus y equals a. I can rearrange that and say something like y equals a minus x. And now we have x squared plus a minus x squared is equal to 25. So I should be able to solve for x in terms of a. Is that something I care to... Yeah, because then I'll get possible points of intersection, and then so what we want is use green here. We use green here. So we'll get these points of intersection. So we can get things like that, which is a tangent, but we'll also be getting things like this. We want to discount these. So what we're then going to do is we are going to connect up the center to these points of intersection, and we should get a perpendicular line if it's... Actually, do I even need to solve this? Hold on a second. Oh, I shouldn't have erased that picture, but okay, whatever. Circle first. So that's less of a good circle. I shouldn't have erased my first circle. Well, second circle, technically. Anyways, so this equation here is y equals negative x plus a. So this is y equals mx plus b form. So we get a slope of negative 1. Yeah, this is going to be much better. Much better. So a slope of negative 1. Now, wherever the tangent point is, it is, as I have already been drawing, on a sort of down and to the right facing line. But if I connect up the center to that point, it should be right angled. So, center is at 0, 0. Slope of center to the intersection point, or tangent point, is the negative reciprocal of our slope here, which is negative 1 over negative 1, which is 1. So the only way we can have these things being tangent is if the intersection lies on the line of slope 1 going through the origin, or y equals x. So tangent point must lie on y equals x and y equals negative x plus a. And also be on the circle. Okay, so we'll have x is negative x plus a, or 2x is equal to a. Or I guess x is equal to a over 2. And then that tells me y is also going to be a over 2. And so x squared plus y squared is 25. So that's a over 2 squared, so a squared over 4 plus a squared over 4 is 25. Multiply both sides by 4. We'll get 2a squared is 100. A squared is 50. A is plus or minus root 50. And we'll answer this on the other page, although it's going to be very quick. So a can be, and I would probably write it as 5 root 2 or negative 5 root 2. But, you know, plus or minus root 50, that would be fine as well. But it was just the a values that they asked for, right? Find all possible values of a. Those are the possible values of a. Okay? And so then x and y are going to be 5 over root 2, 5 over root 2, or negative 5 over root 2, negative 5 over root 2. And that gives us exactly 2 points. All right, so that's 5a. What have we got with 5b? Looks like another circle going on here. So 5b, one side of an equilateral triangle is the 12 centimeter diameter of a semicircle, as shown. Find the area of the portion of the triangle that is outside the semicircle. Ooh. Outside the semicircle. All right. What are we to do? Okay. Well, first of all, if we're going to do anything, we should draw a picture. Draw the semicircle first. I'm much better at drawing straight things than I am at curvy things. Alright, now the first thing that draws my eyes, these points of intersection. So I'm going to connect them up to the imaginary center point. We might even give it a name O. And it's going to divide the diameter in half, 6 and 6. And they did say this is an equilateral triangle, right? Yeah, equilateral triangle, so all these side lengths are 12. Now all these lengths here are 6 and 6. This is 60 degrees. So this one's 60 degrees. So we get a whole bunch of equilateral triangles here. Okay. Not only that, I can even say that this thing right here is 6, and these are 6. Oh, everything's 6. And so these guys are 12 minus 6, so they're also 6. So if we just look at this shape right here, we get a parallelogram with 60 degrees here. It's actually two what do I want to say? Two equilateral triangles. So our blue parallelogram, I messed up that word completely. So our blue parallelogram is just two copies of these equilateral triangles of length 6, side length 6. Now, I don't care about any of this other stuff. I just care about this blue parallelogram. So let's look at it in slightly more detail. So I can figure out the area of the whole thing if I can figure out the area of an equilateral triangle, which I can. Let's make a note of that. So an equilateral triangle of side length S has area of, I believe it's root 3 S squared over 4. I will double check that in a moment. But what we care about here is that we've got the area we want is the area we want, which is outside the semicircle. It was outside that we want, right? Find the area of the portion of the triangle that's outside of the semicircle. So we want this shaded area here. But the shaded area is the parallelogram minus this sector of 60 degrees. Okay. How do I figure out the area of a sector of a circle? If you give me the angle theta and the radius r, this area in here is just going to be, well, if it's in degrees, we'll do it's theta out of 60 degrees times the pi r squared for the full circle. We treat it as a fraction of the whole circle. Okay, so let's just quickly flip to the next page. We're going to verify this formula here. S, split it in half, and 60 degrees. So we get these s over 2, so this is root 3 s over 2 by Pythagoras, or 30, 60, 90 triangles, 30 degrees, 60, 90, have a ratio of 1 to root 3 to 2. So this is just going to be root 3 s over 2. So now it's 1/2 base times height, 1/2 base That's height, and so, yeah, area is root 3 s squared over 4. Okay. So, the area outside the semicircle is 2 times root 3 6 squared over 4, and they did give us centimeters, so our final answer should probably say centimeters squared. 2 root 3 6 squared over 4, those are the 2 triangles that make up the parallelogram, minus the 60 degree out of 360 degrees pi slice of the pi, and the radius here is also 6 squared. Okay, so that's 36 over 4 is 9 times 2, so that's 18 root 3. And this is 1 over 6, cancels with one of those 6's, so it's minus 6 pi. And there's lots of ways to write that. I mean, you can take out the 6, really, and you get 3 root 3 minus pi. But I think as is fine. 18 root 3 minus 6 pi centimeters squared. But we've explained both the formulas we used, the equilateral triangle formula and the sector of a circle formula. We explained that these are both equilateral triangles. I mean, I did it verbally, but you might want a sentence pointing it out, but I'd say it's pretty clear. Blue parallelogram is really all we cared about. It's 2 equilateral triangles, and then the area that they want is this shaded area. Parallelogram minus the sector. So there you go. Not bad at all. It's a nice little question. We're going to flip the page because I don't have enough room for our next question, and our next question is going to be question number 6, which looks like it's going to be very short to read through, but may take us a while. We'll find out. I'll see you guys next time.